Hello, my name's Ahmed Abassi. I'm an applied mathematics PhD student at UC Berkeley in my fourth year, advised by Professor John Wilkening. Today we're going to talk about the semi-analytic theory and computation of Wilken ripples. Our goals are to compute epsilon series expansions of Wilken ripples in conformal space. To do so, we derive iterative algorithms to carry out the computation for the different resonant cases. Then we implement our algorithms on a supercomputer to gain analytical insights and empirically determine whether these series have a positive finite radius of convergence. Our approach begins by proposing an appropriate conformal map to pull back the fluid domain to conformal space, would propose an appropriate ansatz and Stokes expansions for our computations. And then we derive our iterative algorithms and show existence and uniqueness of the solution by showing the algorithms do not break down, and we conclude with our numerical simulations. This is an illustration of the conformal map. This is the non-dimensionalized Bernoulli equation governing the problem. This is our ansatz and Fourier space. These are the regular Stokes expansions without resonance, where the wave crest is defined as the first Fourier mode. This is the equation of perturbation theory, where we use AMP to update the x and p Stokes coefficients at lattice point MP. This is an illustration of the regular algorithm, where we compute the Stokes coefficients point by point, row by row, bottom to top, left to right. And this is the checkerboard symmetry created by the non-zero Stokes coefficients in the irregular problem. Here we introduce resonance to the problem, where the resonance condition is given by the first equation, and the next two equations define the Stokes expansions for the resonant problem, which are an augmentation of the regular Stokes expansions, which we get by adding additional Stokes coefficients as illustrated in the figure at the bottom of the slide. This is an illustration of the algorithm for k greater than or equal to 4, where at each fixed step we need to solve a linear equation to compensate for the main equation of the problem breaking down due to resonance, and the arrows indicate the directions used in the perturbation updates. This is an illustration of the algorithm for k equals 2, where each circled pair of points illustrates a coupled system of two linear equations and two unknowns. And finally, this is an illustration of the algorithm for k equals 3, which is the most involved of the three cases, as it combines aspect of the previous two resonant cases. As for existence and uniqueness, we show this by formally proving using a computer and transcendental number theory that these algorithms do not break down. These are our numerical results for the growth rates of the Stokes coefficients AP versus the order P. And as we can see from the graph, the series expansions do indeed have a positive finite radius of convergence, which can be explained and further analyzed using bifurcation analysis. Thank you so much for listening, and thank you to the ARCS Foundation for generously supporting my research. Thank you.